Alright, now I'm going to go over X-ray tube components and their functions. So everyone's seen an X-ray tube from the outside, even if it's just as a patient. This is what they look like. They're all encased in lead. Other than one small circle, which is right in the middle of where the X-ray beam comes out, because when X-rays are created, they're emitted in every direction. And so this is completely encased with lead that stops any leakage radiation and really only allows a usable beam in the direction that the position indicating device is pointed. And so this houses the X-ray tube, which is where the magic happens. That's where X-rays are created. And it has a power supply, and that's all inside an insulating oil, which helps transfer heat away from the X-ray tube as it's functioning. And then the X-ray tube itself are a cathode and an anode in an evacuated glass chamber. And so we're going to show you schematics of those now. So this is the tube head, as we said, encased in lead, and inside that lead is oil that encompasses the X-ray tube, the power supply, and everything else. And X-rays are created in the X-ray tube. And so that's where this happens. So we're going to talk about each of these components individually. But we have our cathode and our anode, and we'll talk about how this all occurs. Alright, so the cathode is what generates electrons. This is negatively charged. You can think of this like a light bulb filament, but instead of being tailored to produce light, it's tailored to generate electrons. And this is a coil of tungsten wire. It's heated by a low voltage source, and proportional to its temperature it gives off electrons, and that's called thermionic emission. And so that's the first step, is just creating an electron cloud around this filament within the cathode. And here's a mnemonic to remember that the cathode is negative, catnap, cathode negative. Then next we're going to talk about the anode, which is positive. So catnap, just a little mnemonic for you. And the anode, as we said, is positive, so that's where the electrons are directed. And they're accelerated by a very large voltage difference from the cathode to the anode. And that's on the order of 60 to 70 kilovolts. And so that accelerates the electron beam toward the anode. And then it's that bombardment of electrons at the anode in a tungsten target, which is embedded in this copper stem. That's what creates the X-ray photons. So the kinetic energy of these electrons is converted into X-ray photons. And we'll talk about each of the interactions that creates those photons. But this process is incredibly inefficient. 99% of it is lost to heat. And that's because there's so many different interactions that are just not usable. As the electron beam is bombarding the tungsten, they interact with outer electrons of the tungsten atoms and really don't create usable photons. The focal spot is the region on this tungsten target where the electrons are focused. And here we can see a little wear spot at the focal spot. So ideally this would be infinitesimally small. As we know, smaller focal spot means a higher resolution, but there's going to be more heat generated per area or per volume. And so if it were infinitesimally small, this anode, despite being tungsten, having a high melting point, it would just melt. And so there is some degree of area to this focal spot. It's not necessarily infinitesimally small. Alright, and here's the X-ray tube head. As we said, insulating oil conducts heat away from the X-ray tube. The lead collimator, we said this is all encompassed in lead, but then specifically where the X-ray beam comes out, there is a lead collimator to really reduce that X-ray beam to the exact size that you want, which then exposes through the patient to the sensor or the film. So that lead collimator restricts the size of the X-ray beam. There's also an aluminum filter that's placed, and we'll talk about why we have an aluminum filter and why 1.5 millimeters of aluminum filtration is required in any dental X-ray tube head. And then this cone, or we'll call it the aiming cylinder, we also call it the position and indicating device, or PID. That's just to direct the aiming of the X-ray beam so you can see how to line up the X-ray when you're exposing radiographs. As far as X-ray machine circuitry, I don't think you need to know it in great detail. There are a couple things that you do need to know. There's a step up and a step down transformer, or in other words, a step up is the high voltage transformer, which gives you a very high voltage. And where do we want that high voltage? Well, we want it across from where the electron beam travels. So from the cathode to the anode, That's where the high voltage transformer attaches. And then for the filament within the cathode, that is a small voltage that's required, only 3 to 5 volts. And so that has a step down or a low voltage transformer attached to it. And that's regulated by an MA switch. So an MA selector is going to turn up or turn down the voltage across that, which controls the amount of electrons that are generated from that thermionic emission in the filament. Now the high voltage transformer, in most dental settings, it's going to be between 60 to 70 kilovolts or 60,000 to 70,000 volts. You can see in some machines they do go up to 100,000 volts. But typically in the dental world, it'll be on the low end of that range. And this requires a kVp selector, so you can choose the kV. Although in most machines, you don't alter the kVp. They're usually set to about 65 kVp. And then all that we do select is the time, and we change the time of exposure. A couple of important things to recognize. Milliampere is the number of electrons moving through a circuit per second. Kilovolt peak, that is the maximum electrical force or voltage across from the cathode to the anode. Now this is a somewhat advanced topic, but rectification, hopefully you know what an AC signal is, alternating current. That's where a current, just like we get from a wall outlet, it goes from positive to negative and it follows this sine wave. And so you have current flowing in both directions in an AC circuit, and that can be changed to DC. That process is called rectification. One important point is an X-ray tube itself acts as a self-rectifier. Why does it do that? Well, think of the cathode ray tube, which is basically what an X-ray tube is, where you have electrons flowing from the cathode to the anode. The electrons can only flow in one direction. So if the electrons can only flow from the cathode to the anode, that means if you have it set up to an alternating current, when that current is backwards and the anode is actually negative, electrons are not going to flow out of the anode. And so that's what it means by the X-ray tube acting as a self-rectifier. So it acts as a diode, only allowing electricity to flow in one direction. Alright, hopefully you can summarize the X-ray generation steps in your head. First of all, formation of electron cloud. Where does that occur? That's in the cathode. And then the acceleration of the electrons into the tungsten target, so from the cathode to the anode. And then the interactions of that electron beam with tungsten electron is what produces X-ray, and that's what we're going to cover next. That's what occurs in the anode. So a little pause and reflect question for you. Where are the electrons formed in an X-ray tube? Is it anode, cathode, in the patient? Electrons, they come from the cathode. Remember, nap, cathode is negative. That's what has the filament, which emits electrons via thermionic emission. And so where are the X-ray photons formed? Those are formed in the anode. So the electrons are accelerated from the cathode to the anode, and then it's that fast deceleration or the interaction of the electron beam with the tungsten atoms, either the nucleus or the electrons in the tungsten. That's what creates photons, and we're going to talk about that process next. So that was in the anode. And what is the charge of a cathode? Remember, cat nap, cathode, negative. Here's our little kitten napping. So what is the charge on an anode? Again, cat nap, anode is positive.